So in the first part of the lecture, we spoke about how to design a rocket engine to achieve a desired specific impulse. We spoke about convergent and divergent nozzles that can be used to accelerate gases to a high velocity, even supersonic velocities. But we haven't yet spoken in any detail about the different kinds of fuels that we might use in rocket engines. So in this part of the lecture, I'd like us to be able to compare different fuels that we might use in a rocket engine. When we talk about fuel for a rocket, what we're actually talking about is not just the fuel, but the fuel and the oxidant. So the fuel and the oxidant together combust to form the combustion products, which are also the propellants. So the combustion products leave the rocket engine at high speed, thus creating a reaction which propels the rocket forward. Remember what we said before, that a rocket engine doesn't actually breathe in any air. It has to take all its fuel and all its oxidant with it. But that also means that the oxidant doesn't actually have to be oxygen. We can use other types of oxidant as well, as we shall see. So what do we want from our fuel and oxidant? Well, we've mentioned the importance of high specific impulse. A large specific impulse will tend to ensure that our rocket has a large range and payload without having to use a large mass of fuel to achieve that. But there are other characteristics that we'd like from our fuel and oxidant. It will be more convenient if it comes as a liquid, or if it is a gas like, say, hydrogen, we'd want to be able to liquefy it relatively easily. Besides that, it's important to think about safety. Needless to say, rockets and rocket fuels might be dangerous. So some fuels might be less dangerous than others. And are the combustion products of the rocket fuel and oxidant in themselves harmful, either to human beings, or could they be harmful to the environment? So let's think first about the specific impulse. What could we do to increase the specific impulse? Well, we've seen before in the first part of the lecture this graph, which shows two parameters. This parameter we could call a velocity parameter, and this parameter which we could call an area parameter. Both of them depend on the pressure ratio, which changes and decreases as we move towards the exit of the rocket nozzle. A higher velocity parameter will tend to give us a higher velocity at the exit of the nozzle. We already mentioned that the specific impulse depends fundamentally on the exit velocity. Okay, so to a first approximation, the specific impulse of the rocket will be equal to this exit velocity u. So can we maximize this parameter? Well, yes, we can to some extent. If we provide a nozzle with a wider exit, okay, so as we go further and further along this curve, the exit area of the nozzle becomes wider in relation to the area of the throat. The velocity parameter increases, but it's going to be difficult to increase it indefinitely, because for that we would need a very, very divergent nozzle. So in practical terms, we might be limited in how much we can increase the velocity parameter. Perhaps 2 might be a limit. So we could say that the exit velocity is equal to the velocity parameter times the denominator term in the velocity parameter, square root of RTS, which is in itself a constant. So there's 2 things we can actually do. Increase the nozzle exit area, which I just mentioned, in order to increase the velocity parameter, but we're limited in how far we can go. Let's say 2 might be a practical maximum, or we can increase this square root of RTS, and this is where the choice of fuel becomes very important. So we could choose a fuel that gives a very high combustion temperature, TS, or we could increase the gas constant. How can we do that? Well, this gas constant R is not the universal gas constant, it's the gas constant for the combustion products of the particular gases that with the particular fuels that we're using, okay, the fuel and oxidant that we're using. So the value of R will be related to the universal gas constant divided by the molar mass of the combustion products. Therefore, if we choose combustion products of low molar mass, we'll get a higher value of R, a higher value of exit velocity, and a higher specific impulse. So these are two things that we need to look at when we're choosing fuels for high performance. So now let's look at some specific fuels that we could use. So hydrogen. Hydrogen is a very light gas, so it might be convenient as a rocket fuel. It burns with oxygen to form water, which is non-toxic and non-harmful. What else can we say about hydrogen-oxygen as a choice of rocket fuel and oxidant? Well, it has a fairly high combustion temperature of about 3000 Kelvin. The molar mass of the products is 18 kilograms per kilomole. When we put those values into this relation, we work out a specific impulse, ignoring the pressure term in the impulse, of 2,350 meters per second. What else? There's also some disadvantages to this fuel. Hydrogen is a relatively expensive fuel, and it's troublesome to liquefy and store. Okay, so we have to cool down hydrogen to below its critical temperature of about 30 Kelvin in order to liquefy it. It can't just be liquefied by applying pressure. It's a cryogenic liquid. Even when we manage to liquefy it, its density is actually quite low, 71 kilograms per cubic meter. If you compare that to water, water has a density of 1,000 kilograms per cubic meter. So even liquefied form, hydrogen is going to be bulky. We could also use hydrogen with a different oxidant. What about if we used fluorine? So that actually gives us a higher combustion temperature. Okay, TS equals 3,900 Kelvin. Its molar mass of the products is slightly higher, but that's compensated by the higher combustion temperature, and we get a specific impulse of 2,550 meters per second, so slightly higher than with hydrogen and oxygen. We have the same difficulty that hydrogen is going to be a relatively expensive fuel, troublesome to liquefy and store. But not only that, in this case, fluorine is a highly toxic gas. Okay, so it's a toxic gas goes into the engine, and hydrogen fluoride is also toxic and harmful. It's a very powerful acid, even capable of corroding glass. So this is not a very popular choice of rocket fuel, but I wanted to show you it to illustrate how we could use oxidants which are not. So another fuel we could use, which might be more practical, is kerosene. So kerosene is a fuel that's routinely used in jet engines on aircraft, sometimes called paraffin. So kerosene is a hydrocarbon with approximate formula C12H26, and it burns in oxygen with this equation. Okay, so from this we can work out an average molar mass. I would say to work out the average molar mass, we have to work out the total mass of the products on the right hand side of the equation and divide by the total number of moles, 24 plus 26, so it's 50 moles altogether, to get the average molar mass. The combustion temperature is again high, but because of the high molar mass, the specific impulse is a little bit lower in this case, just below 2,000 meters per second. Its products are non-toxic in principle. Kerosene is an affordable liquid. Evidently, it's regularly used in jet aircraft, implying that it's generally available and relatively safe to store and handle. Big disadvantage, the production of carbon dioxide. Surely in the context of counteracting climate change, we'd want to avoid the production of carbon dioxide, so that would seem to be a significant downside. In a table, I've put all these figures together in a table. So hydrogen and fluorine has the highest specific impulse, hydrogen and oxygen the lower one, kerosene the lower, but the variation is not that large. If you go to the problem sheet there's an exercise for you to work out these results for methane and oxygen, methane being another fuel that we could use. So this is all approximate. For a start, I've made a general assumption that the velocity parameter is 2. It doesn't have to be exactly 2, it could be slightly higher, it could be slightly lower. More importantly, what I haven't taken into account is the fact that the molar mass of the products could actually be lower because of dissociation. So when these gases combust, you don't actually get pure water vapor. You get water vapor, some of which is dissociated into radicals like hydrogen radicals, hydroxy radicals, or back into the ingredients of the reaction, the reactants themselves. So this dissociation means that we actually get a lower mass, lower molar mass, and the specific impulse we really get is significantly higher. But the dissociation calculations are relatively complex and we're not going to do those. So I've just used these relatively simple calculations to illustrate how these sorts of fuels are likely to compare in terms of the ordering of them. So that completes our comparison of different fuels for use in rocket engines. In the third and final part of the lecture, we're going to use the results that we've been obtaining in these first two parts to calculate flight range and time for a practical rocket as we could use for delivery of aerosol forming substances to the stratosphere.